Okay, so here's our first video tutorial on Unit 4, which is Chapter 5 in our textbook, Like Terms and Exponent Rules Review. Last day in class, we spent some time looking at algebra tiles, and I wanted to do that for two reasons. The first reason being you're expected to know those for the provincial exam. And the second reason is they're really quite useful. They're concrete, and hopefully that will help us with our algebra. So, like terms and algebra tiles. When we talked about algebra tiles, we had um, like shapes. So, in adding and subtracting with our algebra tiles, what we could do is we could combine the big squares, we could combine the little squares, and we could combine the rectangles, but we couldn't combine them in between. So we could only combine like shapes, squares and squares, rectangles and rectangles. But the other thing that was important, we couldn't combine big squares, the x squared tiles, and the little squares, which were the unit tiles. So when we looked at like terms and algebra tiles, again, this idea of a like shape, but not only like shape, but also the shapes had to be the same size. So pictorially, this was our x squared tile, and this was our x tile, and this was our unit tile. And none of those are like shapes and same sizes all in one. So this is concretely how we represented like terms. Algebraically, the definition of like terms goes something like this. You can look in your book, but I'll describe it as an algebraic expression that is made up of a base and an exponent. So for example, our algebra tiles, we have x squared, we have x, and then the odd one out really is this idea of 1. We'll come back to that one in class. But having a look at the x squared, their algebraic expression, and it has an exponent. Same with the x, it's that invisible number 1. So here's some examples of like terms. 3x squared and 7x squared and negative 3 over 2x squared. All of those are like terms. They have the same base raised to the same exponent. And recall that the numbers in front just tell you how many you have. I have 3x squareds. I have 3 of those square tiles if you want to think about it. Some other examples, 7 over 2x and 3/5 x and negative 17x. Again, these are examples of like terms. They all have the same base and they're all raised to the same power 1, and the numbers just tell you how many you have. And of course, you've been doing like term stuff for a while. 1/2, negative 7, 3 over 2. Those are all like terms because they're just numbers. Okay, let's look at some examples of non-like terms. 3x squared and 7x. 10x cubed and negative 4y cubed. Here's a couple of examples. Now each one of them satisfies part of the definition, but not the other part. So for instance, in our first example, we have the same base, but we have different exponents. In the second example, we have the same exponents, but we have different bases. And remember, the number just tells you how many you have. So here's our definition of like terms and non-like terms. And the only thing I'd like to add for us in grade 10 is sometimes you can get trickier like terms. And when I talk about trickier like terms, I'm talking about clusters. So this is my little word, a cluster. So for example, if we had 7xy, z, our base would be all those letters. And if I wanted to give you an example of a like term to that, well, what I would have to have is the same cluster, the same base. So for example, negative 17x, y, z. These two things have the same base. If we did an example that weren't like terms, where we have a cluster, let me give you 10abc cubed. Well, an example that wouldn't be a like term would just be 2ab cubed c, for instance, or any other variation where we have the same base, but we don't have the same exponents hooked up to each cluster. So for the most part, I'm not really interested in that, but it's a good way of making sure you understand this idea of a like term. It doesn't have to be plain single letters with exponents. Okay. So given that's what like terms are, and again, this is review from grade 8 and grade 9, then the question becomes, well, what can we do with like terms? Well, you can't do a lot. What we can do like terms is we can add or subtract them. That's what we can do with like terms. So let's look at a few examples. And I just want to review a few things to help out. The first thing in simplifying the following nasty looking expressions, we can only add and subtract like terms. And if that's the case, we need to identify them somehow. So again, I try to make it easier on my brain where I look and I go, okay, there's an x squared term. Do I have another x squared term? And here I do there. And I'm going to highlight it in yellow. I notice that I have just an x term. Do I have another just an x term? And I do right there. And then finally, here's my numbers, and here's another number. And what I can do is I can combine those because they are like terms. And when I combine them, I get 3x squared minus 5x squared. Well, 3 minus 5 is negative 2, and I have x squared. I have negative 5x minus 8x, which is negative 13x, and I have 9 minus 11, which is negative 2. So some of the things we have to also be aware of is integer arithmetic. So we have to be able to deal with positive and negative numbers. So not only do you have to identify the like terms, but we have to be aware of integer arithmetic. And remember, help out your brain, somehow identify what the like terms are. So in this example I highlighted, you might not have a highlighter, but here's something else you can do. Maybe you can do a little system of underlining. So in this example on the right, here's my x squared term, here's an x squared term. Here's an x term, here's an x term. Typo, that shouldn't be there. Here is a number, here is a number. So again, I've identified with different lines. Some people put different shapes around them too, and that's all good. So what I can then go ahead and do is to look at my little legend, I guess, and go, what's 11x squared minus 15x squared? Well, that's negative 4x squared. Negative 5x minus negative 8x, well, that's negative 13x. And 11 minus 11 is 0. And there's my final answer. Now, one of the things that might help you out to avoid mistakes like this one, here's a classic mistake. And classic mistakes are good actually because they emphasize something that seems to make sense that is not true. So here's a classic mistake. 3x squared plus 4x squared is equal to 7x to the power 4. And you probably see where that comes from. You add the 3 and the 4, and then you add the exponents, and 7x to the 4. So this is wrong. Here's a really nice way, a really simple way that makes sense, that works for like even little kids. If I wanted to know this, if I change this language to say this, what is 3 apples plus 4 apples? Well, I hope you would say 3 apples and 4 apples are 7 apples. And then I would say, well, what are we representing as apples? And in this particular question, we're representing apples as x squared. And if you do this, you will not make this classic mistake. Okay, so there's a review of like terms and a little bit of integer, a little bit of algebraic addition and subtraction. Okay, and now I quickly want to review a simple exponent rule that we need to know right now in order to be successful in this unit. And our rule is simply multiplying powers with the same base. So if I gave you a numerical example, if I said, what's 3 squared times 3 squared? Well, one of the things we could do is we could break that up into 3 times 3 times 3 times 3. And if we remember our basic exponent rule, the base is the thing we are multiplying, and how many times is the exponent. So in this case, this would be 3 to the power 4. And if you did this on your calculator and you went, well, what's 9 times 9? Well, what you're going to find out is 9 times 9 is 81, and you're also going to find out that 3 to the power 4 is 81. So one of the things you learned in grade 9 was when you multiply powers with the same base, it turns out that you simply add the exponents. So here's the really quick version. By the way, the middle step here is called the extended form, and that's always a good way to do exponent rules. But if I had 3 to the 50 times 3 to the 50, I wouldn't want to write out 3 100 times and then count them all up. So here's our exponent rule really quickly. Let me put it down here where I've put in a place. X to the m times x to the n is equal to x to the m plus n. So this is our general rule. So let me do one more example to illustrate that. Now next unit, after we finish this unit, we're going back and we're going to do a lot more exponent rules. If I asked you what 2 to the power 5 times 2 cubed, let's just do this one. If I expanded that out, well, 2 to the power 5 is equal to 2 multiplied by itself 5 times 2 multiplied by itself 3 times. And if we use the basic definition of an exponent as a repeated multiplication, the base is what you're multiplying and how many times is our exponent. We get 2 to the 8. If you use your calculator, 2 to the 5 is 32 and 2 cubed is 8, and that is equal to 256. And if you punched 2 to the power 8 into your calculator, you get 256 as well. So here's a quick refresher on a simple exponent rule that we're going to use and need to use a lot. Okay, so the last thing I'd like you to do and be prepared to discuss is look at these two statements. And again, these are places of classic mistakes. People get confused between these two. X times x is equal to x squared, that's correct. X plus x is equal to 2x, that's correct. What I would like you to write down and be prepared to talk about next class is how would you explain to a friend the difference between these two so that they actually would understand that these two statements are right. And by that, I mean, don't use a mathematical definition. If someone doesn't understand this, they're not going to understand some sort of definition. Can you come up with a commonsensical explanation of why these two are correct and how you could help your friend?